Good evening. Welcome to the U.S. Geological Survey in another installment of our evening public lecture series. My name is Leslie Gordon, and it's always my pleasure and honor to introduce the speakers each month. Before I do introduce tonight's speaker, I want to make sure you all come back next month. So there are flyers on the back corner table if you didn't pick one up. Our speaker next month is hydrologist Marjorie Schultz. She will be speaking about the marine terraces of California, landscapes from the waves. And any of you that have ever been over to the coast, San Mateo County, Santa Cruz County, you've seen those significant landforms, the marine terraces, and they have a really interesting geological story. So please do join us next month. I know we have many people here that have been coming for years, literally, to our show. And if you have, many of you have actually heard Ross Stein speak before. He's one of our most popular repeat speakers in this lecture series. And so it is my pleasure again to introduce Ross Stein for tonight's lecture. Ross is a seismologist. He's recently retired here in Menlo Park for the USGS. He studies how earthquakes interact by the transfer of stress. He's a consulting professor of geophysics at Stanford University, and as I mentioned, a scientist emeritus at USGS. He is also president-elect of the Tectonic physics section of the American Geophysical Union. Ross gave a wonderful TEDx talk in 2012. I'm sure it's online if you're interested. It was called Defeating Earthquakes. He was also the keynote speaker for the Presidential Awards for Excellence in Mathematics and Science Teaching. And in 2014, he was a distinguished lecturer at the Stanford School of Earth Sciences. Within the USGS, Ross has been roundly recognized. He received the Eugene Shoemaker Distinguished Lifetime Achievement Award from the USGS. He received an Excellence in Outreach Award from the Southern California Earthquake Center, and was also recognized by NOAA with an award called the Outstanding Contributions and Cooperation in Geosciences. So we are very fortunate that although Ross retired last year, geologists and scientists never really retire from the USGS. We just call them emeriti, and they remain involved with USGS and earthquake science. So it is my pleasure to introduce Ross Stein, who will be speaking about the gold rush and the 1906 earthquake, how they combined to create the breakthrough discovery of modern seismic science.
Thank you, Leslie. Let me begin at the ending. Nearly everything we love about the Bay Area is brought to us by the faults. Napa Valley, Portola Valley, and Silicon Valley, Tomales Bay, San Francisco Bay, and Monterey Bay. Absent the San Andreas and the Hayward Faults, there would be no San Francisco Bay, the only deep water protected port along the California coast, and so the wellspring for the gold rush. The Hayward Fault lifted up the Berkeley and Oakland Hills, giving spectacular sunset views of the Golden Gate. Faults make Big Sur big. A bend in the San Andreas thrust up the Santa Cruz Mountains, the spine of the peninsula, and the Marin Headlands. These coastal ranges temper our climate, bathe us in fog, and crown us in redwoods. What I want you to see is that we enjoy the fruits of the faults every day. And so we have to learn to live with their occasional spoils, as befell the Bay Area in 1906 and 1989, and the Southland in 1857 and 1994. While we cannot predict earthquakes, we know where the hazard is high and we know why it's high. And we can erect structures to withstand any shaking that the Bay Area faults can throw at them. And this is what we must do. So tonight, we'll move from the discovery of gold to the discovery of what an earthquake is, and from there, how earthquakes interact, which is highly important for the Bay Area. And so I'd like to begin this story with showing you the world, or the home planet, as it was given to us 50 years ago in the plate tectonics revolution, where the discovery was made that the surface of the Earth is not fixed and rigid, but highly mobile, with about a dozen great plates moving around from fractions of an inch to several inches a year. Where these plates pull apart, these yellow zones, basalt is welded onto the trailing edges, and where the plates collide, these magenta zones, are the great subduction zones of the Earth. And what happens there is that the denser of the two colliding plates gets shoved under the lighter one. And this is where the world's greatest earthquakes occur. Now, profoundly important for the discovery of plate tectonics was the 1906 earthquake that occurred 60 years beforehand. This was the first realization that the surface of the Earth was mobile and active. But that discovery never would have been made had not the gold rush occurred 60 years earlier. And it's that story that I'd like to begin the evening with. So here it is, the two-paragraph announcement in the Californian in 1848, announcing that gold had been discovered. And it's kind of an amazing line at the bottom. It's like they are foretelling the tech boom rather than the gold rush. So that's incredible foresight. And as soon as the Federal Army confirmed and assayed the gold, 60,000 people around the world abandoned their jobs, their families, and their communities and boarded ships to sail to San Francisco. And they were right, because within 2 years, all of the arrivals were getting the dregs. The real lucrative gold finds occurred in those first few years. And so here's how it was supposed to work. There'd be some miners out there at Mile Rock, and you just wave the ships in with a hanky. But it didn't really turn out that way. And that's because if you've ever been outside the Golden Gate, you'll know that it has the fastest currents anywhere on the coast, faster often than these boats could sail. It has steep waves, high winds, and often dense fog. And so many of these ships, after having come halfway around the world, came to grief in the Golden Gate. And so the federal government sent out surveyors from the Coast and Geodetic Survey to create decent navigation charts, because this is the chart that was used in 1851. It looks nothing like the California coast. And the idea, and this is part of the chart, was that the captain was supposed to line the ship up so that they could see Alcatraz in the middle of the gate and then just shoot the rapids. And it just really didn't work out that way. So what's interesting about map making in the 1850s is that you could not measure a long distance. Once you came to the end of a tape, you were done. And in fact, we couldn't measure long distances until the 1970s with the development of the laser. What you could measure were angles. So what was done is you'd use a theodolite and you'd go to a promontory or a mountaintop and you'd measure an angle to two other mountaintops. And thousands of these angles would be measured, and that's how locations were determined. Because the instruments were heavy and inaccurate, every 5 or 10 years the surveys were repeated with better and lighter instruments. They saw changes in those angles, which they attributed to better instrumentation. So that map making continued, but there's something interesting about what happens when you're measuring angles to make a map. And let me illustrate it this way. Let's say I put a square on a balloon, and I inflate the balloon, and the square gets bigger. Do any of those angles change? No. Expansion and contraction was invisible to them. They had no way of measuring that. Now what happens if I shear that square? Now two angles have gotten smaller and two larger. So as crude as this measurement was, they were very sensitive to shear. And that accident changed everything. Now, this is the map that they made that was completed in 1856. And this beautiful map is as accurate as any we have today, despite how crude these measurements were. And what I love about this geodetic map is it actually has sailing directions in it. And you can also see San Francisco during the gold rush. Let's zoom in on that. So here's the city in 1853. It had already burned to the ground twice by this time. And the city had gone from 15,000 people to 100,000 people in a year and a half. So when that city burned down, that was quite a conflagration. Now you see a couple of things. You see the marina on top. You see Yerba Buena Cove, which we've never heard of, and Mission Bay. These were where the gold rush ships dropped anchor. And to give you a picture of what Yerba Buena Cove looked like at that time, here's a contemporary photograph in 1851. By the way, look how built up San Francisco is at that time. Now, when I look at this picture, I count about 70 ships in 1851 in port at anchor. Now let me show it to you 2 years later, in 1853. It's hard to count, but there are about 700 ships in this picture. Now here's what's really interesting. Take a closer look. These ships are a wreck. They're falling apart. So here's what happened. These ships would travel halfway around the world, the most lucrative merchant line anywhere. The passengers would disembark and jump onto steamers and head to Sacramento and from there to the gold fields. And so would the crews. Every single crew member abandoned ship because they could earn 10 to 100 times more in the gold field. And not one captain was able to raise a crew to sail the most lucrative route back and pick up more passengers. Every one of these ships rotted in place, completely abandoned. And eventually, San Franciscans simply imported sand from what is today Golden Gate Park, dumped it on the ships, and that is the financial district. So here is one of these ships unearthed in 2001 between the Transamerica Tower and Portsmouth Square. And look at Telegraph Hill. Look at what the city looked like in 1851. So let's come back to that map. And let's compare it to what San Francisco looks like today. So you can see San Francisco has really grown quite a bit. So what do we see? What was Yerba Buena Cove is now part of the banking boom. It's the financial district. What was Mission Bay and its marsh is now Soma, part of the tech boom. And what was the marina, another place where ships dropped anchor, is now the center of the dating boom. And that's what we've inherited. And this turns out to be San Francisco's Achilles heel. Because this junk land, to put it kindly, shakes and liquefies in earthquakes. And this is where the greatest damage was in 1906. And because we didn't learn our lesson, it was where the greatest damage was in 1989. And it will be a problem again. So think about that when we see this enormous boom going on in the Soma area. But all this changed on April 18th, 1906. Now, the most powerful words ever written, contemporary words written about this earthquake, were penned by Jack London, who wrote for Collier's magazine 2 weeks after the earthquake. It was published on May 5th. And what I'd like to do, as I show you some of these images, is just read a passage from Jack London's report. San Francisco is gone. Nothing remains of it but memories and a fringe of dwelling houses on its outskirts. Its industrial section is wiped out. Its business section is wiped out. Its social and residential section is wiped out. The factories and warehouses and great stores and newspaper buildings, the hotels and the palaces of the nabobs are all gone. Remains only the fringe of dwelling houses on the outskirts of what was once San Francisco. On Wednesday morning at 5:15 came the earthquake. A minute later, flames were leaping upward. in a dozen different quarters south of Market Street, in the working class ghetto, and in the factories, fires started. There was no opposing the flames. There was no organization, no communication. All the cunning adjustments of a 20th century city had been smashed by the earthquake. An enumeration of the buildings destroyed would be a directory of San Francisco. An enumeration of the buildings undestroyed would be a line and several addresses. An enumeration of the deeds of heroism would stock a library and bankrupt the Carnegie Medal Fund. An enumeration of the dead will never be made. All vestiges of them were destroyed by the flames. I went inside with the owner of a house on the steps of which I sat. He was cool and cheerful and hospitable. Yesterday morning he said I was worth $600,000. This morning, this house is all I have left. It will go in 15 minutes. He pointed to a large cabinet. That is my wife's collection of china. This rug upon which we stand is a present. It cost $1,500. Try that piano. Listen to its tone. There are few like it. The flames will be here in 15 minutes. There are no horses. And he was right. Everything was destroyed. Nothing was left. After the earthquake, which nobody understood, nobody in the United States understood that an earthquake was an explosion, an implosion, nobody knew. Geologists from Stanford and Berkeley started to walk the path of destruction north and south of San Francisco. And what they saw were things like this: a tear, a rent in the landscape. By the way, this is Alice Eastwood, who saved the botany collection of the California Academy of Sciences during the earthquake. And even more startling, they discovered that wherever they found this tear in the landscape, anything that crossed it was offset. So a road or a fence line or a stream. So these orange points were originally side by side. And what they noticed was whichever side you're on, the other side has moved to the right, which they called right lateral. And they saw that the amount of this displacement varied from about 6 to 12 feet, but over the entire 250-mile-long rupture, this is what they saw. And they realized for the first time that an earthquake involves permanent displacement of the land. Then they realized, wait a minute, we need those triangulation measurements to be redone, because we need to figure out, is this what you see? And as you move away from the fault, do you also see this 12-foot offset? So the geodetic survey came back, and they surveyed points that they had last surveyed in 1905, in 1906 and 7. And if you put a dotted line down perpendicular to the fault, and you slide all those displacements that they measured from promontories into their position at the same distance from the fault, you can see, yes, there's 12 feet of displacement across the fault. But as you move farther away, those diminish. So it's like the ground had leaped ahead along the fault, but as you got farther away, you began to see that diminish. And then H.F. Reed from Johns Hopkins University said, wait a minute, let's go back and look at those surveys that were done from 1851 all the way up to 1905 and see what we can learn from those. And he found something truly astonishing, which was that those points had been moving all along. There had been no movement along the fault during those years, but there was plenty of movement as you moved away from it. So if you look at the motion of the Farallones out in the west compared to Mount Diablo, they were moving at about an inch a year in opposite directions from each other. So this was an indication that the earthquake wasn't the whole story. The land was always moving, but it wasn't moving along the fault. And so if you line up those points along this dotted line, what you see is that the entire area was being sheared. Now remember, I told you that triangulation measurements are uniquely and exclusively sensitive to shear. So this was pure serendipity. Not only that the measurements were there from 1850 to 1905. So you could see this accumulation of strain, but that they could detect that strain with such a crude instrument. And so here's how Reid put it together. He said, well, if it's moving at an inch a year, imagine you let a couple hundred years go by and you'd see about 12 feet net movement between the Farallones and Mount Diablo. Then we're going to add the earthquake displacements on top of that. And now you see something really simple. The fault has just been offset. So the fault doesn't leap ahead, it catches up. The whole thing has been shearing, but it's stuck along the fault. And suddenly that frictional resistance is overcome and the fault catches up and we simply have an offset on the fault. And that's the earthquake machine that we have. And that's what Reid discovered, and that has been confirmed in everything that has happened since. So with Reid's inheritance, we can look at the Bay Area and say, it's not just one fault, but we have lots of faults, including the Hayward, that gave us the magnitude 7 in 1868. And when we look at all these faults, they all have this right lateral motion because they're all in this giant shear system. And what happened in 1906 is the biggest player of those faults, the San Andreas, had its event. Now, Reid had these crude tools, but what Reid was telling us was, look, you don't have to wait for the earthquake to come to know where the hazard is going to be high. What you should be doing instead is measure the strain everywhere you can on Earth. And today, with GPS, we can measure displacements extremely accurately everywhere. We have 20,000 GPS receivers around the world, and here is what we now see in terms of the distribution of strain on the globe. So this is the Japanese subduction zone, and at the bottom you see where the 2004 Sumatra earthquake occurred. Oh, what happened to my globe? We have a thief. I spent so much time painting the boundaries on, but what I want to show you is that the plate tectonics view of the globe is not the whole story. I drew these lines, but what you're seeing here is that the deformation extends well into the continents. In the oceans, yes, it's a thin line, but in the continents, deformation extends way in, as do our faults in the western US, extending all the way to the Wasatch. And so the picture with great data that's since collected gives us a much richer sense of where earthquakes have occurred and where they will occur in the future. In the center of the picture, you're seeing now the North Anatolian Fault, that bright line, and that gave us the most spectacular falling domino sequence of earthquakes ever recorded between 1939 and 1999. And here's our piece of the tectonic puzzle, the San Andreas system you can see working its way through California with a branch that goes up the eastern side of the Sierras as well. Okay, what I want to do now is take that view that I just gave you and make it a little bit more real, because you will see that the system that we inherited from Reid can really be simplified down to what I'm going to show you now. So the interiors of these plates are moving every day at a fixed rate. The plates get hung up on their boundaries, and that's why we have earthquakes. So this casting reel represents the steady motion of the plate's interiors. This rubber band represents the rubberiness, the elasticity of the Earth's crust. If the Earth's crust weren't elastic, we wouldn't have earthquakes. I'll grant you it's very stiff, elastic material, but it's elastic. And then here are some granite slider blocks that are going to be the guys that are affected by the earthquake. And this surface is just a non-skid, just industrial non-skid. Okay, so I'm going to crank steadily. I'm not going to do anything to create earthquakes, and I just want you to watch. Okay, So you saw that there would be a couple hundred years, then we'd have an earthquake, and we wait maybe 100 years, then, right? So in fact, there's nothing I can do to prevent this from producing earthquakes. I can't just make it slide. It's going to produce earthquakes. Okay, now here's a question for you. Were they all the same size? You're sure about that? That's very bad news. If I can't make regular repeating earthquakes with Home Depot sandpaper, a rubber band, a casting reel, and kitchen countertop samples, we're never going to get it in the earth. That is the bitter pill that we've swallowed from 30 years of research on the behavior of earthquakes. We can never talk about a fault as being 10 months pregnant. They are not that regular. And what's interesting about that observation is when you think about it, that irregularity can't come from this because I was steady. It can't come from the rubber band because it's always within its elastic range. It can only come from the friction, which means even though when I put my hand over this it feels extremely regular, tiny little irregularities cause faces of the fault to get hung up. And when those grains pop, things begin to happen. And it's remarkably unpredictable exactly when they're going to let go. So that lack of earthquake predictability is a fundamental part of the earthquake machine. But that doesn't mean we can't do anything. We can do tons. So let me ask you another question. What if we just have a one-bricker spot? Am I going to get more earthquakes or less if I'm cranking at the same rate? Are they more frequent or less frequent? Are they going to be smaller or larger? Okay, so let's see what we get. So they're about twice as frequent, right? And they're about half the size. And that makes sense when you think about the fact that the motion is being resisted by the weight of those bricks times the friction. The friction isn't changing. So if I have the weight, then there's less resistance and it can go forward. And we have a one-bricker place on the San Andreas. It's called Parkfield. It knocks off earthquakes every 20 to 40 or so years, and their sixes are 6.5s. So it's interesting to think that same elasticity, same friction, same speed of the San Andreas an inch a year, but I can get places that produce 6s rather than 8s. If I can just find some places that are only one-brickers, and we haven't. Okay, next question. We've sandblasted the bottom of these samples to create the friction. And the top side has the original polish. So what if I just turn it over, so the polished side is down? Now I've only changed the friction on one side of the fault. The other side of the fault is the same. What's going to happen? Okay, let's see. It's very interesting, right? It's almost just creeping, but it's producing lots and lots and lots of little earthquakes. Well, we have such a spot on the San Andreas. We call it the creeping section. It extends from Hollister down to Parkfield. It's 100 miles long, and it basically moves every day, and it produces more earthquakes than any other spot on the San Andreas, and it's only got low friction on one side. One side is granite, one side is serpentine, which is very, very mushy, plate-like material. Now, you might also say, well, now, wait a minute. There are not that many faults in isolation. The San Andreas is 700 miles long. So what about faults interacting? So now what I'm going to do is I'm going to hook these guys up in series and ask you to tell me who's going to go first. And then I'm going to ask you who's going to go second and who's going to go third. Okay, so who thinks this guy's going first? All right? Who thinks this guy's going to go first? All right? Who thinks this guy's going to go second? Who thinks this guy's going to go third? Okay. All right, for those of you who are willing to bet, okay, here we go. Gets interesting in a hurry, doesn't it? Okay, so first it was a total trick question, and you never should trust a speaker. This guy went 3 times, right, before he was able to tension this guy up to go. But once this guy did get that tension going, this guy went, and sometimes when that guy went, they all went together, and sometimes they didn't. And that's exactly what faults do. In general, we have independent cases, but we had in 1992 in Southern California, the Landers earthquake, where 4 wannabe faults joined up together and produced a magnitude 7.3. Faults we never thought could have ruptured together produced a very large earthquake. And so sometimes that happens, sometimes that process happens in 20 seconds, and sometimes it happens in 20 years. And that variability further complicates the business of predicting earthquakes because no little earthquake is marked for future greatness. It doesn't know it's going to be a big one. Most of them don't make it, and occasionally they do, and we can't figure out which of those ones, which of those little earthquakes that are actually going to cascade into something much larger. But all is not lost because there's still something very important about the condition that tells us that once we've had an earthquake, we can say something about what might happen next. Okay, so if I get this thing almost ready to go, what's going to happen if I lift a brick? Everybody feel that way? Good. Okay, so I unclamp the fault, right? And the San Andreas is like that, but same deal. I've unclamped a little bit, so it makes it easier to go. And by the same token, if it's just about ready to go and I pull on the spring, I can trigger an earthquake, right? But if it's just gone and this thing isn't tense, oops, that didn't, it's suction, okay? Nothing? Nothing. So only if faults are very close to failure do they become sensitive to the combination of increasing the shear stress or unclamping the fault, which is called the Coulomb criteria. So if we can calculate that in the field around an earthquake, we can say something about where the aftershocks are more likely to occur and where the next larger shocks can occur. And that is our way in to a very hard problem. That's the easy way in to a very hard problem. Yes?
Are you taking questions?
I'm taking yours.
What natural phenomenon is equivalent to lifting a brick?
Okay, great question. So imagine the San Andreas, which extends 10 miles down.
What's the question?
Oh, I'm sorry. She said, well, what's the physical phenomena of lifting a brick? And lifting a brick is whatever process will allow a fault to unclamp. So if some other earthquake in the neighborhood creates some kind of tension perpendicular to the fault, then that stress will be lowered. If it's a subduction zone like this, maybe you're subtracting material above it. So anything that changes the stress which keep these faces under enormous stresses in close contact will tend to promote failure. Okay, so now we're going to go one step further. So this was the one-dimensional view of life, which is my favorite dimension. And now we're going to go to 2 dimensions in a series of animations to take you a little farther into this world of earthquake interaction. And we're going to do this for the North Anatolian sequence because that's that falling domino sequence of earthquakes. And that is a clue that earthquakes interact, and so we want to be able to explain that. So we're going to go to the site of the last earthquake in the sequence in 1999, put up the fault, and we're going to put a fence across the fault, just as you saw across the San Andreas. And we're going to watch 200 years of stress accumulate, and you can see that that bends because the whole area is being sheared, and then suddenly the fault ruptures and it catches up. Exactly what I showed you that Reed discovered, right? The squares sheared into parallelograms, the earthquake occurred, and they unsheared. Okay, and so that's the earthquake cycle. So far, so good. Now the question I want to ask is a little different, though. I want to say, what about beyond the ends of the fault? Okay, this guy's had its earthquake. Beyond the ends of the fault, if this fault continued, have we brought that fault closer to failure as a result of this one, or farther? And that's a question we have to understand. So I'm just going to repeat this experiment, but rather than just putting a fence across the fault, I'm going to put a whole grid. densify the grid, and watch stress accumulate. And let's focus our attention just beyond the end of what will be a blue rupture. And does this shearing parallelogram get more sheared or less after the earthquake? You can see it's more, and if we color more sheared red, we have this kind of blowtorch zones beyond the end of the rupture. The blue areas are places where we removed some of that stress. Now here we've stretched this guy. This is where we've lifted a brick and lifted a brick here, and here is where we've added a brick here and here. And if we add those two together, we get the Coulomb stress. So what it says is if there's a fault out here, this guy is now closer to failure as a result of the neighboring earthquake, as would be a fault over here or over here. But a fault here is in what we call the stress shadow, this profoundly blue zone where we've reduced the likelihood of failure. Okay, now let me just show you one other way, same deal. So these are these places where we've pulled on this spring. These red zones are just where we've done this. And then here where we lifted a brick, here and here, or added a brick, and we multiply this panel by the friction coefficient, which for most rock materials is somewhere around 1/2. And we add them together and we get the Coulomb failure condition. So now let's try this out on the North Anatolian fault, but we'll first try it out on just a simple ironed out fault. But I'll put each rupture on, and what I want you to see is that each rupture has a blowtorch zone beyond the end, and that seems to be where the next rupture nucleates and then propagates. So we can see how we could get a falling domino sequence of earthquakes. Now let's try it out on the real fault. Real life is a little bit more grungy than that, but the process is the same. So we have this zone that gets filled by an earthquake out beyond 1943, 44. Both of these spots will get filled by earthquakes over here, 57. Then we're going to get the 67 in here. This turns it red where the August 1999 earthquake occurs. Now that turns this guy red, which ruptured in November. Okay, so you can see how earthquake interaction is a helpful tool to understand what can happen next. But now I want to show you something, tell you something very important about this. This map is basically turned blue. In other words, if we have any parallel faults, and remember the Bay Area is a series of parallel faults, then they're all in the stress shadow, and they've all been shut down. Okay, so now let's go back to the slides to see how this plays out in the Bay. So this is the record of earthquakes in the San Francisco Bay from the start of occupation by the Spanish. And what's astonishing about this 75 years is that magnitude 6s and 7s are ricocheting around the bay. 2 magnitude 7s, one on either side of the bay, and lots of 6s. Now compare that to the 75 years after the 1906 earthquake. Almost complete shutdown. When we calculate the stress transmitted to those faults by the 1906 earthquake, you can see that the bay fell into this profound seismic shadow, which probably explains the shutdown of earthquakes, which means we've been living in a very unusually quiet period for the bay. Now, the gods continue to crank the casting reel, right? That rubber band is getting tighter, and we have 110 years of cranking that's going on. So our best realization of what the stresses look like today are about like this. And because the stress has profoundly dropped the most on the fault, the stresses work their way in from the sides. And so you can see that the Hayward Fault in the East Bay and to the North Bay, we have some very high stresses building up, which is why we have to concern ourselves with being prepared for the next earthquake. We are almost certainly moving into a period where we will see more earthquakes because these stresses have come back and the whole area is shearing. Okay, so I'm going to take you to the new Bay Bridge, but I think maybe this is a moment for a little bit of gallows humor. See, you have choices no matter what. Okay, so here's the Bay Bridge. I mean, here is the paragon of seismic design. And why so? Because it has a tall, slender column or mast that takes the compression loads. It has stainless steel cables that take the tensile loads. It's light on top and it's heavy on the bottom. Except I'm not talking about the bridge. I'm talking about the boat. Oh, no. That's right. The boat is made of light, strong materials, fiberglass, aluminum, stainless steel cable. It's built with triangles and curves, which are inherently stronger than a cube. And it's heavy at the bottom and extremely light on top. And here is the incredible thing. There is not a sailboat in the bay that could not withstand anything that the San Andreas or Hayward Fault could throw at it. And you're saying, oh, well, that's just because they're bobbing around in the water. No, you're wrong. If you dug a hole in the ground and you hoisted any sailboat into the ground, that boat would do just fine with the largest earthquake you could put on it. And it's even better than that. It's not just structural damage to the boat. If we go inside one of these boats, you're going to see that in the galley, which is the sailing term for kitchen, or the saloon, sailing term for the dining area, that there are no sharp corners, there are handholds everywhere, there's no glass that could fly around, every drawer is latched. Does this look like your kitchen? Probably not. In fact, the stoves are gimbaled. You could make soup during the Loma Prieta earthquake on any boat in the bay. Okay, so I ask you, how could naval architects be so smart and architects be so stupid? Well, it's really that the Darwinian process of natural selection in boat design works really fast compared to building design. Anybody who designs a boat and sends it out into the bay on a summer day, you know, with high winds and a lot of chop, that boat, if it isn't built for it, is going to the bottom. And that design isn't going to do very well. And so quickly, yacht designers learn what is necessary to make a vessel that can handle these very, very high accelerations. And it's even more true for boats that go offshore. So this is a part of the design. It's not built into any boating codes. It's boating sense. Now compare that to buildings. Very few architects have ever experienced a large earthquake. And it's not in anybody's experience or anybody's life preparation. So they're basically building to codes, and the codes produce only the minimal safety standard. So I want you to compare this kitchen to any bar you choose in the Bay Area. So here's one that I chose because it's local. I'm a field scientist, so I do a lot of research and have to go out and sample everything. But look, we know what's going to happen in an earthquake in that bar, right? It's going to be horrible. And is this bar in any kind of problem location? No, everything's fine. It's a mile from the San Andreas. So here's your homework assignment. I challenge you to go to any bar in the Bay Area that restrains the liquor bottles. Now, I spent a lot of time in Japan. Actually, in bars in Japan. I've never been to a bar in Japan that does not restrain its liquor bottles. This is denial. Okay, I have to make one back step. There is a kind of boat that doesn't meet any of the glorious standards that I described, and it's called a houseboat. And if you took this thing out on the bay on any summer afternoon and turned it broadside to the wind or the waves, it's basically going to keel over, all those windows are going to break, everything's going to fall apart, and it's going to sink to the bottom. So if there were justice in the world, that would be its naval architect being pooped out the transom. Okay, guys, here's the bad news. We all live in beached houseboats. And let me tell you what I mean by that. Here's a building that you'll find anywhere in the Bay Area and pretty much anywhere around the world. We have decided to build buildings out of stacks of cubes. Cubes have no structural integrity. They're only held together by their corners. no matter, this is bolted down to the ground, actually Velcroed. And no matter how strong I make the columns and the beams, this building is only as strong as its corners. What's going to happen in an earthquake? The ground goes side by side. And also torsion. See how weak this building is? If you don't believe me when I say cubes have no structural integrity, look at this. IKEA house. You can put it in your station wagon and drive it home. Okay, this is the exact same building, but I've snapped in, literally snapped in these little corner braces with sewing snaps. Watch. Nothing. Okay. How much more do you think it takes? What do you think the additional cost is of building this building than this building? Any guesses? 1% to 2%. And if you're retrofitting this building to go to this building, maybe it's 2 to 3%. So this is what we have to do. This is how we have to live. And this is incidentally why a boat is strong, because it's filled with triangles and curves, and it's not a stack of cubes. So as long as we want to build tall cubes, we are facing an incredibly difficult engineering problem. It's ironic to think that if we lived in geodesic domes, we would not be having this seminar, because nobody would care about earthquakes, because they wouldn't kill anybody. But we have chosen buildings that attack us. And so we have to move away from that. So I want to leave you with the idea and the recognition that so much of the wealth and beauty and history of California is bound up in its seismic setting. And so we, in a sense, in a very real sense, serendipitously and ironically, the Bay Area's loss has been science's gain. How much was learned from our seismic past. And the best way I, as a scientist, can return this to you is to try to encourage you to move from this to this and work to make yourself safer for the earthquakes that lie ahead. Thank you. And I just want to point out, seismically strong buildings can be absolutely beautiful. And I also want to acknowledge the people who made these wonderful tools with me.
I'm sure many of you have questions, and Ross said that he'd be happy to answer them. We do have 2 microphones in the 2 aisles back here. We'd like you to use a microphone not only so others in the room can hear you, but we're web streaming this live so people online can hear you as well. So if you can, please line up at 1 or 2 of the microphones and we'll go back and forth. If it's difficult for you to do that, wave at me and I'll bring you a microphone. But why don't we start with the gentleman in the orange shirt? Go ahead with the first question.
It's going to be a funny question. Where do you stand on fracking then? That's supposed to be relieving and making small earthquakes. Does that make it better, worse, or who knows?
So the USGS actually is doing a lot of work in trying to understand the role of oil field and gas field activities in inducing earthquakes. First, you should know that 18 months ago, Oklahoma dethroned California as the most seismically active state in the Union. We're very upset about that, taking it very personally. And most of these earthquakes are almost certainly induced, but they're not induced by the fracking per se, which is happening at rather shallow depths. They're induced by what's called produced water, all the water that comes out of the ground with the gas and oil and the fracking fluids that need to be re-injected very deep into the ground so that they don't contaminate the groundwater. By injecting under high pressure these very toxic fluids, they're reaching fault zones. And as long as the rubber band is sufficiently tight, these are not fault zones where the crank is cranking very fast, but it is still cranking. So some of these faults are close to failure, and basically they're being lubricated, and or moderate to large earthquakes are occurring. Yes? Oh.
Go ahead. Do you discuss the program that USGS and Caltech and Berkeley have regarding early warning detection for earthquakes?
Sure. So earthquake early warning is a very exciting development on the horizon for all of us here that can give us seconds to tens of seconds of warning before earthquakes. And there's a great deal that can accomplish in terms of dropping fuel rods in nuclear reactors and stopping laser eye surgery, and the list is long. However, and so this is important, and many different groups are working to bring this to fruition, and many parts of the world already have such a system. With that said, remember that none of us want a situation in which we all got warning and every building fell down. We do not want to have to rebuild the Bay Area. We want to build it strong. So the proper combination of things is to have early warning, but then also to recognize that we can take steps so that when that earthquake occurs, it's not just a matter of preserving life safety, that we have a habitable, recoverable community. Yes?
So 2 questions. The first one is, do you see any future long range in lubricating faults from what we're finding out about fracking, and therefore avoiding big quakes? That's
Well,
question 1.
you know, careful what you wish for,
Yeah.
is all I can say. You know, it's certainly true that, and it's been known since the 60s, that lubricating faults can trigger earthquakes, but you don't know. Here's the problem. It's a numbers game. So let's say what we're trying to do is get rid of the 7s. Well, a 7 is 1,000 times larger than a 5. So you need a 5, you need 1,000 5s to get rid of that 7. And so you simply can't get enough moderate earthquakes to remove the importance or the need for the larger earthquakes. So in a world in which we could lubricate all the faults, we'd have big earthquakes every day to get rid of the likelihood of something really large. And it's just as possible that by lubricating the fault, we will actually create the large earthquake that we would rather avoid. And there's evidence from filling of reservoirs that large earthquakes have occurred in that fashion.
And you said that the nature of earthquakes wasn't really discovered until they started observing the displacement from the 06 quake. Was Japan any further ahead on this? Did they know what was going on since they've had
There was
so
an
much
earthquake
history?
in Japan in 1894 called the Nobi earthquake, where the Japanese began to see similar things. The 1906 earthquake was so much larger and so much better surveyed that the message was really kind of burst into awareness around the world. So the Japanese, as they are often today ahead of us in seismic science, began to see things just before we did, but the picture immediately snapped into focus after 1906. Yes?
Okay, I heard that the One Rincon building had a ballast of water at the top to counter the sway from an earthquake. Would that work, do you think?
So I heard that too, but then I talked to an engineer recently, and of course I'm not an engineer, and I was told it does not have this water baffle system. However, I was in the Taipei 101 building, which is really, this is the Taiwanese definition of the word chutzpah. They built a 101-story building at the foot of a fault in the path of typhoons.
Oh my gosh.
Okay, so at the top of this incredible, beautiful building, it's got this beautiful kind of bamboo-like look to it. The Taiwanese call it a stack of Chinese takeout cartons. But at the top of it is a giant steel ball as wide as this room that's suspended and has dashpots at the bottom. And this is designed for an earthquake or a typhoon that if the building tilts over, the ball then goes out of alignment and the ball sucks the building back into position. But what's really great about this is you're going to kill me about this, there's a bar around the ball, and you can sit there with a cocktail, and you can watch this ball displaced. And you go, oh, I'm 100 stories up, and if that ball is moving, it means actually I'm moving. So I think that's one of the best geological experiences you could ask for. Yes?
So I'm curious about the development of the tectonic theory and why, after they noticed the the ground slippage, why did it take so long for them to extrapolate that, hey, this thing actually would go on and on and on, and then suddenly you'd have faults all over the world? So I don't know if you know anything about that.
It's a great question. What was really powerful about Reed's discovery is if you could move 12 feet on a fault every 200 or 300 years, then in 10 million years you'd move 150 miles. And that was inconceivable at the time. The thought was the only way the Earth could change is if it expanded or contracted. And this didn't make any sense. So like many things in science, some powerful clue lay there kind of waiting, germinating for other ideas to come along. And Wegener's hypothesis of continental drift had the continents plowing through the oceanic material, which geophysicists couldn't stand because they couldn't see how lighter material could actually move through the denser oceanic material. So it wasn't until submarine data began to reveal, and oceanic data began to reveal the nature of the seafloor and these mid-ocean rifts, they were put together with earthquakes like 1906 and the 1966 Parkfield earthquake, and things snapped into focus. And like most discoveries, once those pieces started to assemble, everything happened really fast. Everything happened in a matter of a year or two. It was all over between 1966 and 1968. And this is just as profound as natural selection, this change of thinking.
Thanks.
One other question.
I saw you before.
I know. I heard the Northridge earthquake was a new kind of blind thrust fault. Was that known about before? Or if it wasn't, how many more don't we know about?
So blind thrust faults were something that began to be clear between about 1980 to 1983 when we had the Kalinga earthquake. That was the first large blind thrust earthquake of magnitude 6.7 in the oil patch in east of the San Andreas. And there had been a magnitude 7.5 earthquake in Algeria on a blind thrust fault too. And it just means it's blind to the geologists. The fault doesn't come to the surface, so you can't map it at the surface. And what it does is it folds the rocks at the surface. And so now they're detected by finding places where the strata have been warped or folded. And so many of the important blind faults now are part of the USGS models and other models around the world, but they are the hardest faults to find, and I'm sure there are more out there. And I might add, in my 30 years of being a geologist and standing in front of the news after an earthquake, about 1 of every 3 earthquakes occurred on a fault we didn't know about. This is a very humbling field, okay? If you want to be smug, choose another field, because this happens over and over again, even without blind thrust faults. Yes?
You mentioned in the case of loading a reservoir or injecting fracking fluid, you seem to mention lubrication as the primary driver for earthquakes from these things that humans do. How would you consider lubrication versus loading for what's the primary driver of those earthquakes?
It's a great question, and they're probably both important. The Wenshan earthquake in 2008 in China, which was a magnitude 7.9 and killed 60,000 people, 20,000 of them school children. The epicenter of that earthquake was underneath a reservoir that the Chinese had recently filled. And there is some evidence that the filling of that reservoir, possibly by both diffusion of water and lubrication and changing of the load, might have been the factor that triggered that earthquake. The Chinese, of course, very vigorously deny this possibility, and the evidence is not overwhelming. You don't see a sequence of earthquakes migrating to the future epicentral site. So there are lots of cases of earthquakes that are associated with dams up to magnitude 6.7 and this possible one at 7.9, but it's very hard to be certain of those relationships. So undoubtedly both processes are important, and the point is, your point is well taken.
Thank you.
one of the slides you had of the Bay Area showed the Hayward Fault in kind of an orange and then another fault off the shore, but the San Andreas outlined in blue. Would you explain what that means for the future of the San Andreas?
Well, you know, imagine that the San Andreas slipped a uniform amount, then the stress shadow would be all about the same along the fault, and the San Andreas would be kind of the last to go because it has gone most recently. But the fault is not a straight line. It's got bends and breaks, and the slip is irregular, so there are probably concentrations of stress on the San Andreas that we don't know about that could give us 6s and 7s on the San Andreas. The San Andreas did have on the peninsula near Filoli, there's evidence for a magnitude 7 in 1838. So we know the San Andreas does not just knock off 8s, or actually 7.8s, it also produces moderate earthquakes. So it's very difficult to know what it could do next. But let me put it this way, no seismologist would be shocked if the San Andreas, any part of it up here, produced a 7. It's just part of the game. Yes?
So you mentioned about the early warning system. How do they work? Are you measuring strain, or are you measuring early movement somewhere more closer to the epicenter, or is there something else?
It's a great question. Basically, it's just another geo trick since we can't predict earthquakes. So we get enough instruments out there that we can detect the earthquake as it's rupturing, as it's beginning to nucleate. And just so you know, an earthquake nucleation is a process where the fault is normally moving an inch a year, and it speeds up to 3,000 miles an hour in about 3 seconds. This is one of the reasons why these things are so hard to predict. If you have instruments close enough, you will detect that. If you have 3 or 4, then you can be certain that it is not a disturbance or a malfunctioning of one instrument. So those associations are made, the determination of the earthquake, and then as it starts to grow, its size becomes evident, and then there's enough computer power to determine roughly when that shaking will reach everybody, and then on your cell phone you'll have an app for that, and you'll get a ring, and it'll tell you how strong the shaking should be for you and when it'll get there. Now, this is in testing now, and it's a far cry from fail-safe or bulletproof. There are missed earthquakes, there are false earthquakes, there are false alerts, but the system is really just a matter of detecting the earthquake and getting that to you before the seismic waves do, because they're moving at 3,000 miles an hour, and they're going to get there more slowly than that signal.
All right, just a follow-up question. I heard of some experiment with electromagnetic disturbances that were detected, I think, 1906 or 1989, and I mean, there's a theory that, okay, there might be some electromagnetic disturbances before that we could. Do you have any thoughts on that?
Well, the USGS isn't pursuing that line of research. There are some independent groups that are looking to see if there is a consistent and reliable indicator of that kind. But I want to say that that's why I called it a bitter pill to swallow. Just about everything we've tried hasn't worked. And the best evidence from the laboratory and the field is that if we're thinking about a magnitude 6 or 7 earthquake, the preparation zone, if there is one, is about the size of this room. And it's 10 miles down. So it's a pinprick. And being able to detect that phenomena on the surface of the Earth is extremely difficult. Parkfield, the place I mentioned, the one bricker spot, so we kind of know where it was going to be because it kept happening. We put everything we had at Parkfield. It ruptured on the other end of the fault than we thought, so our best instruments were about 15 miles away. We could measure tiny changes in pressure. We could measure pressure changes that would be equivalent of dropping a jigger of gin in Lake Tahoe. And we saw nothing before that earthquake. Nothing whatsoever. So I invite you to work on this problem because it is hard and it needs young people to make progress there. Yes?
This is a question regarding your non-collapsible model that you have on there.
My good guy?
Your good guy, yeah.
Yes.
Do the USGS scientists and geo advisors partner with construction firms to create some type of seismic retrofitting standardization? Because it seems like the only people doing the testing are the manufacturers of the parts. And if you call any local contractor to get input on how they approach retrofitting your home, it's all over the map, including cutting more parts away of your foundation rather than adding, in layers on the exterior frame.
It's a great question. So the survey, USGS is not involved in this process. There's the Earthquake Engineering Research Institute and the Applied Technology Council, and to some extent the California Seismic Safety Commission, all of which address this. There's also Earthquake Brace and Bolt, which is administered by the California Earthquake Authority that gives retrofit grants and are focusing on research on retrofit. But I completely agree with you that overall the retrofit business is a mess. There is no licensing for retrofitting. I just want you to know, you cannot color a woman's hair without a license. You can retrofit a home without a license. That makes a lot of sense. And it's worse than that. I just refinanced, or my wife and I just refinanced our home, and the California certified real estate appraiser came to my house, and I said, his name was Joe, I said, Joe, would you like to know if I've retrofitted my house? And he says, no. I said, what do you mean no? He says, it has no effect on the value of the house. So this is a broken part of the system. And so you put your finger on something. If we can standardize it, if we can accredit it, if we can properly train for it, this is a relatively inexpensive fix. For most of us, $5,000 to $10,000 that confers an enormous increase in safety and survivability and loss of reduction of damage. So thank you. Okay, I think this is our last question.
I have a question about the new reservoir in China that was blamed for the earthquake. Was not that earthquake inevitable anyway? And could that reservoir have possibly lessened the damage?
Well, certainly the first part of your premise is correct. That this is a fault that is being loaded, its spring is being pulled, and so it would have an earthquake sometime anyway. So at most, filling of the reservoir advanced that earthquake by perhaps 100 years. But certainly, if that's your family, that 100 years really matters. So if you're going to change the natural process, then you're going to put yourself into a situation where you could be blamed. In Hawaii, if a lava flow goes down the flank and it engulfs a home, there's no liability issue. But if you deflect that lava flow, then anything else that happens downstream, you're responsible for it. So I think that it's an issue of responsibility, and it will be very hard to prove one way or another, but the larger problem is this, and we should just end here. In countries like India and China, to fuel their magnificent economic engine, they need water and power. And where do they need to build these reservoirs? In the foothills, which are laced with faults in both countries. So they are not really being straight with the public because they feel they have to produce the water and power. And as a result, we are seeing hydroelectric facilities go up in places where inevitably we will be in harm's way. That's the larger problem. Thank you for your wonderful questions, and good night.
Thank you, Ross, and thank you all for coming. And some of you probably noticed there was a little slip of paper on your chair when you arrived. We don't usually ask for well, we're always open to your opinion, but tonight we're explicitly asking for it. You can leave your responses on the table in the back of the room if you care to give us your opinion. Thank you, and I'll see you next month.